Okay, I hope you people have the notebook and pen ready with you. Okay. Yes. Okay. Cool. So we are going to start discussing sets, and I'm planning to complete sets and relations today because functions itself is a very big topic. Because in addition to our understanding and the proper definition of a function using relations, we also study functions extensively, learn to find their domains, ranges, other operations. So we'll keep functions for the next class. Today let us study sets, relations, and at the once the theory discussion is over, we can go to MCQs. Acha. So we will first start with the definition of a set. Briefly or quickly, what is the definition of a set? A collection of well-defined objects. That's what we study in school. Okay, we can just say collection of objects. Now the symbol. Okay, all these objects, whatever they are always written in between two curly brackets. So that's the notation. Okay, notation. Okay, this is the notation. The elements come here. And the letters that we use for a set are generally uppercase letters. Uppercase Roman letters are used for representing sets. Okay, A, B, C, etc. And the members of a set are called elements. Members of a set. And what notation do we use when I want to say that this particular element is actually belonging to a set? I'll use this notation. Say 2 belongs to the set of natural numbers. This epsilon, that's a letter from Greek script. We also use it for permittivity, but here we say belongs to. Okay, and if I want to say that something does not belong to that set, okay, I'll say 3 by 2 does not belong to the set of natural numbers. Is that clear so far? Okay. Now, when it comes to representing sets, including its elements, we have 3 ways. Okay. The representation of a set consists of 3 ways. Okay. First one is called the list form or roster form. Second one is called the set builder form, which is more popular. Set builder form. And the third one is using Venn diagrams. Okay, the third one is using Venn diagrams. The representation of a set using Venn diagrams is useful, especially in probability. Okay, it is useful in probability where we consider events to be sets, right? Where we consider events to be sets. Fine, so let us take one common example and write it in the list form, set builder form, and using the Venn diagram form. Okay, so let us start with the list form. I'm going to consider 2, 3, 5, 7. Okay. In the set builder form, I can say A is the set of all those values of x such that x is a prime number, or x is a single digit prime number. We can say x is a single digit prime number. Okay, is it clear? That is the set builder form. Quite often the set builder form is more useful, especially when we want to represent a set which has infinitely many elements in it. Okay, and how can we represent it using a Venn diagram? A Venn diagram always wants us to have what we call a universal set. So if I reconsider this to be the set of natural numbers, it could very well be the set of prime numbers for that matter. Okay, let's say this is the set of all prime numbers, and among them we consider only those 4 which are single digit, 2, 3, 5 and 7. Okay, 2, 3, 5 and 7. And this set, which is quite often represented by a rectangle or a circle, that is the set E. Okay, any doubts so far? Okay, no doubt. The other use of Venn diagrams is in learning relations. When we learn relations, okay, let me omit the word learning here, relations, and also functions, when we define functions formally as a special class of relations. Correct? There what do? There we draw these elliptical diagrams, if you remember. Okay, we have a set P, we have a set Q, and then we draw arrows, and then using those arrows we decide whether whether it is a function or not. Okay, so Venn diagrams, we use them in probability, we use them also in the relations and functions. Okay, can you guys quickly write all these things down so that we can go to the sets of numbers? Be quick. And once you are done, let me know. Let's now go to sets of numbers. This is also important for other topics. We have this hierarchy of numbers. I'm going to represent it again using Venn diagrams. Okay, so we have complex numbers here. We have complex numbers here. The set C denoting complex numbers. Now I will always draw a vertical line and I want to distinguish it from a letter. So this is the letter C and this represents the set of complex numbers. Okay, so the set of complex numbers C. Under it we have the set of real numbers. We have the set of real numbers R. Okay, within the set of, rather the set of real numbers is divided into 2 categories, you know that. First one is a rational number and the second one is a irrational number, right? So we have the set of rational numbers here. I am going to define them later. So this is rational number Q. Then the set of rational numbers is divided into the set of integers and non-integers. So here we have got the set of integers. The standard letter that we use to denote the set of integers is the letter Z. And within the set of integers, what do we have? We have the set of whole numbers. We have the set of whole numbers. And within the set of whole numbers, we have the very first set that we learn in school, and that is the set of natural numbers. Okay, so let us write these things down in the list form or in the roster form, and whenever possible or whenever that is preferred, we will also use the set builder form. Okay, we will also use the set builder form. Point 1. Let's begin with the set of natural numbers. Set of natural numbers. What is it? 1, 2, 3 and so on. Okay, 1, 2, 3 and so on. Second, we have the set of whole numbers. In the set of whole numbers, we only have one extra element which we do not consider to be a natural number, and that is 0. 0, then 1, 2, 3 and so on. Okay, and from now onwards, when it comes to the set of, when it comes to the set of integers, let me write it here. When it comes to the set of integers, we still prefer to write it in the list form. -3, -2, -1, 0, 1, 2, 3 and so on. But after this, when it comes to the set of rational numbers, we usually prefer the set built form. Okay, so what is that? X such that x belongs to p by, or x is equal to p by q, sorry, x is equal to p by q, where p and q are integers and q not equal to 0. Do you remember or do you understand this definition of rational numbers? Yes? Okay, rational, we have real. Okay, so can any one of you tell me how can we define irrational numbers? Okay, how can we define irrational numbers? Any idea? Yeah, exactly. Uh, yeah, okay, that's one way to look at it. That's right. Not equal to p by q. Numbers which cannot be represented as ratios of two integers are all irrational numbers. But within irrational numbers, we make two categories. Ones which are roots of polynomial equations with integral or rational coefficients, and the others which are not. Okay, so let us add one more point here. Consider x squared minus 2 equal to 0. Okay, consider x squared minus 2 equal to 0. So here we know there is no rational number x which can satisfy this equation. So x equal to root 2 or x equal to negative root 2. This is what we call an irrational number. So irrational number, okay, it is still a root. It is still a root of a polynomial with rational coefficients. Okay, so all the numbers of the kind root 2 or cube root of 5, or let's say 100th root of 69, etc. So we can actually build an equation whose coefficients are rational numbers and whose roots are these, and you need not always have them in this form. They can very well be in the form a plus root p or a plus nth root of p. Okay, their general form. Or well, you know, now you can just modify this, play with it, and come up with other forms. So these are still roots of a polynomial with rational coefficients. Do you people understand what is a polynomial and what are rational coefficients? Yes? See, okay. A polynomial in X is basically an expression of the kind a naught plus a1x plus a2x squared plus a3x cubed and so on. Okay, this is in general a polynomial. Okay. Now because our definition of rational numbers is very clear, we can very easily say whether a polynomial is a rational coefficient when possesses rational coefficients or not. What are the coefficients here? A naught, a1, a2, a3 up to a. So when these are rational numbers, we call it a polynomial with rational coefficients. Make sense? Huh. Now all those numbers, okay, all those numbers which when plugged in as x give us a 0 are called the roots of that polynomial or root of that polynomial. Okay, and if this root is not a real not a rational number, then we have to call it an irrational. Okay, so it is still a number. We can actually plot it geometrically. Like for example, in the school days, you must have plotted root 2, right? There is 0 here, there is 1 here, then you build a right triangle which is simultaneously isosceles, then you put your compasses sharp edge at origin, okay, then you measure the hypotenuse, it's root 2, and then you take that circular arc and this is the root. Okay, so you know the precise way to plot all those irrational numbers. Okay, but in this set, in this particular set, let me highlight it in blue color now, where we do not consider any rational number, there also lie many other numbers, okay, which we call actually irrational, but there is a separate class of them. Do you know what those numbers are? Those numbers are called transcendental numbers. Okay, those numbers are called transcendental numbers. Okay, I can give you two examples of transcendental numbers. First one is E and the second one is pi, but there are many such numbers. Okay, so what are these? These are never roots of any polynomial with rational coefficients. Okay, so if you try to form a polynomial whose coefficients are always rational, okay, whose coefficients are always rational, then whatever real roots that it is going to have, those roots will always be irrational numbers, but they will never be of this particular form, E or pi. Okay, well, you can still form an equation like this. Look, you can still form an equation like this, a quadratic equation whose roots are E and pi, which are transcendental numbers, but here the coefficients are not rational. Do you realize what I'm trying to say here? You can build a polynomial whose roots are transcendental numbers, or numbers like E and pi, which are not exactly irrational. But my main point is, the polynomial that you have built does not have rational coefficients. It has at least one of its coefficients is not a rational number, like E pi, we know they are not rationals. Is that clear now? So which means we can partition the set of real numbers. We can partition the set of real numbers into two things, in which we will include all transcendentals on one side, like E, then we have pi, etc. And then all irrationals, which are actually roots of a polynomial with rational coefficients, they come here. Roots of polynomials with rational coefficients. Okay, so we have got this hierarchy from the set of natural numbers to whole numbers to integers to rational numbers and irrational numbers, and we have some transcendental numbers, and then finally we have complex numbers. What is the definition of a complex number? Okay, what is the definition of a complex number? A number of the form x plus iy, where x and y are real numbers, and by definition I or iota, which is square root of negative. Okay, so I want you to revise and keep these things in mind, and I want you to never forget these. The set of natural numbers, the set of whole numbers, the set of integers, the set of rational numbers, then irrational numbers and transcendentals. Some books consider transcendental numbers as rational, but some books don't. They make two different categories. The numbers which are roots of polynomials with rational coefficients, they call them, and are not rational numbers themselves, the roots, we call them strictly irrational numbers. And then roots, the numbers like E or pi, or there are many other numbers, but at this level only two of them we will consider. We call them transcendental numbers, and then we have the set of complex numbers. Okay, one last point before I give you time to write. In mathematics, the word integral is sometimes used as an adjective of integer. Okay, and the word integral also means the integral from calculus. Okay, so I hope you know how to decide whether it means as an adjective of integer or the calculus integral. Yes? Integral values of x, what does that mean? Integral values of x mean the values of x which belong to the set of integers. Okay, and consider the following integral a to b. That basically means the integral in the calculus part, and they are different, they are not related to each other. Okay, so it could also be there could also be a question, is the value of this integral an integral or not? That is also a question. Is the value of this integral? So here the first integral is this, okay, but the second integral is this. Okay, hope you understand that the difference between the two. If, well, you might already be knowing it, but if you don't, then please make sure that you correctly interpret what's being said, or by what context, in what context the word integral is being used. Okay, quickly take a note of this, then we will go to next part. Fine. Does anyone know what is a null set and what is a singleton set? Yes. Yes. No elements. Singleton set. Only one element. Any examples for a null set? Any example of a singleton set? Yes. Just come up with an example that will help you in thinking, I would say. Any example of a null set? No, that is the way we represent it. That's fine. But I'm saying, can you come up with a situation? Okay, can you come up with a situation, or preferably you can say an equation. It doesn't have any root in it. Okay, so let's say A is a set of all those values of x such that sin x is greater than 1. Okay, that is a null set. Sin x is greater than 1, but because it can never be greater than 1 as long as x is a real number. Okay, any example of a singleton set? Any example of a singleton set? Okay, let me come up with an example here. Look. Okay, the set of values of x, okay, such that y is equal to x squared and dy by dx is equal to 0. Is it a singleton set? It is. Why is it a singleton set? Because the function that I have chosen, okay, the function that I have chosen is a parabola, or it has a parabolic curve. And if this function y equal to x squared has its derivative 2x, which is equated to 0, produces only one value of x. And what value of x is that? That is equal to 0. Correct? So can we call it a singleton set? Yes, we can. Is that clear? Huh. So I think when I keep on saying that they mix concepts from multiple topics, this could be an example of that. So they might ask a possible MCQ like this. Possible MCQ. Which one of the following is a singleton set? Now, most of you will be knowing what a singleton set is. But if they give you conditions like these, then you need to know calculus, or then you might also be required to know coordinate geometry. Or if I change this function y equal to x squared to some other complicated function whose graph we cannot visualize easily, then that problem immediately becomes difficult. Not because you do not know what a singleton set is, but because it takes you some time to grasp how to handle that particular situation which is inside the set. Is that clear?
Yes, sir.
Yeah, correct. So that could be a possible MCQ. Which of the following is a singleton set? It will have 4 options. Okay, next. Subset, superset, proper subset and power set. Acha. Now I will not define these things very clearly, well explicitly, because you people already know what a subset is, I assume. Suppose A is 1, 2, 3, 4, 5. Then any other set which contains where all elements of B, if they belong to A, then B will be called a subset, right? So if I say B as 2, 3, 4, I write B as a subset of A. Okay, so the symbol of is a subset of is U rotated in the clockwise direction by 90 degrees. Okay. Now the actual symbol of a subset also has a line below that U. Can you tell me what that line is for? Yes, do you know what that line below the the inclined U is for?
So, for subset.
No, this is a proper subset.
No.
Okay, see, a proper subset means number of elements in B has to be less than number of elements in A. When that is the case, then we call it a proper subset. Okay, but if I'm saying that my set C is the set of all those natural numbers less than or equal to 5, then C also becomes a subset of A. C also is a subset of A. But here, number of elements in C is equal to number of elements in A, but simultaneously the elements that are present in C is they are exactly same as that present in A. So here we call it, so we still write C as a subset of A, but we want to emphasize that C actually contains all elements that are present in A and nothing else, not more than that. So therefore we add that horizontal line here. Okay, so proper subset means that particular set will always have at least one, will always have some elements in A which do not belong to that set. Okay, I hope you understand that. But when I want to say that every set is a subset of itself, then I will use this symbol. I will use this U tilted clockwise by 90 degrees, and I will also use this symbol. It's pretty much the same as less than or equal to. Okay, or a greater than or equal to. Here we also want to cover the possibility of x being equal to 4 or x being equal to 3. Just like that, in a proper subset, it is equivalent to strict inequalities, x greater than 3 or x greater than 4. But when we also want to include the equality there, we change the sign to that's being a subset of and this. Getting the point? Yes, okay. Correct. So we call B subset and we call A the superset. Okay, and if A is not equal to B, then B is called proper subset. Okay, and what is power set? Does anyone know what a power set is? No, that is the size of a power set. But what is the definition of power set? the set of all subsets is the power set. Yes, you're right. There is a formula to determine the number of subsets. And what do we, you Koina already had stated that formula. If A has n elements in it, then the power set of A is going to have 2 raised to n elements. Do you know how to prove it? Yes or no? Exactly. So once in a while, you should also take a look at proofs. Okay. The reason being, when you go to any institute like IISER, you are supposed to prove things in mathematics. Well, to be able to apply the formulae, that's right, that's a good thing. Okay. But that, I would say, is kind of incomplete understanding, because you don't know how to prove that formula. Okay. Of course, this course is not intended to provide the proofs of the results that we use, but this being our very first encounter with such a situation, let me come up with a proof for this, and you will see how other topics should be brought in order to prove this very simple result. Okay, so why does a set with n elements has 2 raised to n subsets? Look, suppose I name these elements as A1, A2, A3, so on till A. Okay, now I convert this subset problem into a counting problem. I ask the question, in how many ways can I pick m elements out of n? Of course, without repetition, because in set theory, or in set basically, we, even if 2 comes twice, we do not consider it twice. Okay, we just consider it once. Okay, without repetition. Now you might be knowing the answer to this question. The answer is NCN. Is that right? Or in some books they use this notation, NM. Yes. Okay. Now if I set m equal to 0, I will get my null set. There is one way to do that. That is null set. If I set m to 1, there are n ways to do that. I will get n singleton sets. Correct? I will get n singleton sets. And if I set m equal to 2, then how many ways are there? We write it as nc2, then 3, we write it as nc3, and so on. So if m becomes equal to n, then it becomes NCN. NCN, and that is again equal to 1. So this is the set A itself. Okay. Now you might ask, see, now this is basically the number of subsets that we have got. So we need to add all these things, and these are binomial coefficients you might be aware of. So it is nc0 plus nc1 plus nc2, so on till ncn. This is the total number. And to prove that the value of this is 2 raised to n, what we do is we first use the binomial theorem. It is nc0 a raised to n b raised to 0, nc1 a raised to n minus 1 b raised to 1, nc2 a raised to n minus 2 b squared, nc3 a raised to n minus 3 b cubed, so on till nc n minus 1 a raised to 1 b raised to n minus 1, and the last term ncn a to the power 0 b raised to n. And in this binomial theorem, we put a equal to 1 and b equal to 1. And by doing that, all these terms all of them, they become equal to 1. But what happens to LHS? LHS becomes 2 raised to n, and therefore RHS is 2 raised to n. So in binomial theorem, if we put a and b as 1, we get 2 raised to n. That is the sum of the binomial coefficients. So from this, we go back to this. And that is what we have used, or that is what we have got from this question that we set. It's a counting problem, and that is as good as solving this particular problem. Okay, so we did not expect that. We did not expect that in the proof of how many subsets can a set have, we are required to use binomial theorem and counting principle. Okay, so if you keep your vision open a bit wider and not very rigid that I'm only going to solve problems on set theory or relations, I don't want anything else to be included in that, then unfortunately that is not the case. Is that clear? That's my point. And hereafter, if you are looking for a proof for any other result in mathematics, a theorem or an inequality, you can expect or you can borrow results that you have studied from other topics. Is that clear? Not only for 11th and 12th mathematics, but also beyond when you take up other courses, higher level courses. Okay? Fine. So you can skip writing the proof right now, but the point that I was trying here is the demonstration of multiple topics involved in a proof. Okay? Okay, fine. Can you write all these things down, please, in a moment? Fine. Let us now go to union of two sets. Okay, so what is A union B? A union B is a set such that X belongs to A, or X belongs to B, or X belongs to both sets. Okay, if I want to represent this in terms of Venn diagram, okay, if this is my set A and if this is my set B, then A union B would be this set. Okay, if you want to find an equivalent operator or operation in propositions or in reasoning, it would be OR. Okay, P or Q, either this or that or both. Okay, intersection, how do we define it? X belongs to A and X belongs to B. Okay, so what is the Venn diagrammatic representation of this? Simple. This is A, this is B, and A union A intersection B is this set. Okay, let me use green marker here. This is A union B. Sorry, A intersection B. Okay, and this, the corresponding equivalent thing in logic is P and Q. Okay, now when do things get complicated? Just like we have defined A union B, we can also define A union B union C. Okay, so you can try that as homework, or let us do it here. Let's do it here. Can we show A union B union C on a Venn diagram? We can, right? We can show that. Suppose I want to show A union B union C. I will basically highlight everything that belongs to that. Okay, so let's say this is A, this is B, and this is, suppose, C. Okay, suppose this is C. Okay, I will also need this for my A intersection B intersection C, so let me paste it here. Acha. Now what should I do for A union B union C? I should not leave even a single space. So whole of A will be there, whole of C will be there, and whole of B will also be there. Okay, but what about A intersection B intersection C? only that part which belongs to all three of them will be A intersection B intersection C, and I can extend this idea to multiple sets, not necessarily or not only to two sets or three sets. If I want to consider A union B union C union D, I can also do that. Is that clear? Huh. Now, apart from set theory, can you recall any other instance where we use this A union B union C? Recall the definition of collectively exhaustive events from probability. Do you remember that? So if I have n such events and if I take the union of all of them, I will get the universal set X or the sample space. Okay, so there we actually use this. And what about this? Where do we use intersection? Can you think of any, I would say, example from probability itself where we use the intersection of three things? No, in exclusive, you say that the intersection is a null set. That's right, that's fine. The events are mutually exclusive. But when we want all three, okay, when we say all three events have occurred, probability of occurrence of all three events. Simultaneously, right? When all three events appear simultaneously or occur simultaneously, that basically is number of elements in A intersection B intersection C divided by the number of elements in the sample space. Am I right? So in probability we can make use of Venn diagrams, and if you have seen my other videos, whenever it is a Bayes theorem problem or a problem of probability, I tend to solve it by this approach. Okay, that's my way. You people may have some other approach. Okay, but keep your eyes open and always try or always think, have I seen this or have I applied this particular concept from set theory somewhere else? That will help you realize or understand the links that exist between different topics. Okay, is it clear? Okay. Okay, now what about complement? It's very clear, right, for a complement? Complement of a set. Exactly, universal minus S. So this is complement. This is a complement. Some textbooks use A bar, some textbooks use A prime. I'm going to use A C. That's a complement. Okay, complement of a set. The equivalent thing in logic is negation P. In logic we say, or in reasoning we say negation P. Right, so whenever P is true, negation P is false and vice versa. Okay, and Danish, when you said mutually exclusive events, any set and its complement is always a null set, correct? And in probability this means the events are mutually exclusive. Understand? Yeah. Okay, you people can write this down, and then I think that almost ends the discussion on sets. I want to tell you one more formula, and then maybe we can go to relations. The universal set is like the master set. So currently what is the master set of numbers? The set of complex numbers. Every number that we are going to see or we shall see, that will belong to complex numbers. Okay? Fine. Now let me tell you a principle. Have you heard this, the name of this inclusion exclusion principle? Okay, you know, you already know it. You must be knowing this formula. Number of elements in A union B is number of elements in A plus number of elements in B minus number of elements in A intersection B. Yes? You might also be knowing this formula in A union B union C. Can you tell me the formula? Na plus Nb plus, correct, A intersection B, correct, minus Nc intersection A, correct, correct. Now if I ask you, I have union of n sets, what's the formula? Okay, and that general formula is called inclusion exclusion principle. Not going to prove it and also not going to state it, but you should know this. Okay, the proof involves mathematical induction. Proof involves mathematical induction. And see, in mathematics, we always try to generalize things. You must have seen that. Okay, we always try to generalize things. So we do consider some special cases or some simple cases, but at the end, the objective is always to come up with a formula or a theorem which will cover a wider variety of problems. Okay, so that is the fancier name, inclusion exclusion principle. And this also becomes addition theorem of probability. When you divide this one by the number of elements in the sample space, that becomes addition theorem. Okay, so this is a precursor of addition theorem of probability. Okay, and write this down, and then we will go to relations. Relations now. Fine. Now this is where we begin to advance from just sets to, well, higher level. So the first term that we learn is called Cartesian product of two sets. Okay. The first term that we must know is an ordered pair. So an ordered pair A comma B is such that unless A and B are same, A comma B can never be equal to B comma A. Okay, the sequence in which we write the components matters. That is an ordered pair. The generalization is ordered n tuple. Okay, so ordered pair is there, ordered triple is there, ordered quadruple is there. So in general, we have ordered n tuple. That's the word. A1, A2, A3, so on till An. Okay, let us first define Cartesian product of two sets. What is the notation? The notation for Cartesian product of two sets is very similar to cross product. Okay, how can we define it? It is the collection of ordered pairs A comma B such that A belongs to set A and B belongs to set B. Okay, similarly, can you tell me the Cartesian product of three sets? It will be A into B into C. So it will be the set of ordered triples A, B, C such that A comes from A, B comes from B and C comes from C. Is that clear?
Yes, sir.
Huh.
Yes,
Now,
sir.
yeah, okay. Now can you tell me how many elements can a Cartesian product have? If I say that size of A, size of B and size of C is known. Suppose Na is equal to X, Nb is equal to Y and Nc is equal to Z. Then how many elements can we expect in A cross B? We have to apply multiplication principle. If we take first element of A, it can be paired with all elements of B. So this is XY. Number of elements in B cross C will be YZ. And number of elements in A cross B cross C will be XYZ. So there we are using multiplication principle of counting indirectly. Clear?
Yes.
Okay, if you want you can write these things down. Alright. How can we define a relation? Okay, we consider Cartesian product of two sets only, cross B. So any subset of A cross B is a relation from A to B. Okay, you might already know that any subset of A cross B is called a relation from A to B. Now, if there are X elements in A and Y elements in B, how many relations are there? Can you tell me that? Number of relations from A to B? Sorry? See. So this is where we are going to combine two concepts from the same topic. First, we know that if a set has 3 elements, then the number of subsets of that will be 2 raised to 3. So definitely this has to be 2 raised to something. And if we want to say, if we are saying that it is a subset of A cross B, do we know how many elements we have in A cross B? You have told me, Danish, it is X into Y, correct? So essentially the number of relations are the number of subsets of A cross B by definition. So that is 2 raised to XY. Now, did you understand that? Okay. Okay. So 2 raised, see now, this is where we have moved one step ahead. We knew everything that we wanted individually. We knew the definition of a relation. We knew how to determine number of subsets of a set. But when we borrowed these two concepts, we got a new result. Now you know that this result is very easy. Number of relations from A to B is 2 raised to X into Y. Okay? Now let us give this a thought. What is the significance of these things? Apart from studying different types of relations, and that is a whole new topic. But have you ever wondered why is relation so emphasized in mathematics, or at least at this level? Because after this we never use it. Its significance is to rigorously define a function. Well, we might say that function is a rule that connects two sets and other things like y equal to sin x connects R to R. But through relation we can define a function, and every other definition will kind of fall into it. Correct? So how do we define a function as a special case of relation? Every element of the first set has a unique image in B. That's how a function is defined. For relation, there is no such restriction. Is that clear? Yes. Fine. So we will write this down. Then we can. Okay. Let me give an example here. Suppose A is 1, 2, 3, and suppose B is X, Y, Z. Okay, it's not X, Y, Z. Let's take alpha, beta, gamma, delta. A, this is B, 3, alpha, beta, gamma, delta. So let me connect 1 to alpha, 2 to alpha, and it's not necessary that in a relation I should connect 3 with everything else, okay, or even I can connect 1 with multiple elements. Okay, so if I want to define a relation R1 from A to B, and if I want to write it in the set form, list form, I'll say 1 comma alpha, because there exists an arrow which leaves 1 and meets alpha. Then 1 comma delta, and also 2 comma alpha. Then there are terms related to this. Okay, the first set is always called the domain. The second set is always called the codomain. Okay, now when I say that one is related to alpha, alpha becomes the image of 1 under R1. Okay, but beta is also an image, sorry, not beta, delta is also an image because 1 is related to delta also. So delta is also an image. Okay, so do you know what 1 is called as? 1 is called as pre-image. Yes, 1 is called as pre-image. Yeah. And what is range? Range is the collection or the, okay, let me be precise here, set of images. So range of R1, can anybody tell me range of R1? Very good, I'll find it. That's it. Is that clear? Yes, you can take it. Yeah, you can take it down. Okay. Well, do you realize this? Yeah, do you realize this? Any curve in the xy plane, any curve in the xy plane is a relation, or the set of all points there. Sorry, let me put it in that way. Okay, any curve in the xy plane will consist of points, right? Consist of points. So there, and their coordinates. They always form a relation. No matter what curve you take. You take a circle, you take a parabola, you take a rectangle, you take an inequality, everything. That will always form a relation. Correct? And only some of them will be called functions, and then we have certain tests to determine whether the given relation or given curve represents a function or not. Okay? Alright. Binary relation, do you know what a binary relation is? Yes, what is it? A relation defined on the same set, right? A relation defined on same set. Okay, so if A is a set, for a binary relation we do not need anything else. Okay, for binary relation we do not need anything else. Any subset of A cross A will be a binary relation. Understood? Okay. Now we are going to discuss three types of relations. Okay, we are going to discuss three types of relations. First one is reflexive relation. Now please remember that these few further types of relations that we are going to study, these are all binary relations. Okay, so let me add that here. Okay, the special types, namely reflexive, symmetric, and transitive, they are always binary relations. Okay, fine. Any okay, do you people remember the definition of a reflexive relation? What is it? No, 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 not that. Okay, so R is reflexive. Okay, fine. Let's say, suppose we have set A. and a relation R is defined on A. Now on A means on A cross A. So what is a reflexive relation? R is reflexive if A comma A belongs to R for all values of A in A. Okay, let me make it clear now what I mean by that. Suppose A is 1, 2, 3, and suppose I say R1 as 1, 1 and 2, 2. Now why is R1 not reflexive? Yeah, exactly. It does not involve 3, 3. Because 3, 3 does not belong to R1. Whereas R2, see, it may have additional pairs, okay? It may have additional pairs like 1, 3, doesn't matter. It's reflexive. So if you have this idea in mind that a reflexive relation can only have those ordered pairs whose components are same, that's not the case. Okay, that is not the case. So this is also reflexive. Is that clear?
Yes.
There is a very nice way of representing reflexive relations using matrices. Okay, look. I need to build a square matrix and whose size will be equal to the number of columns in it and rows will be equal to the number of elements in it. Okay. Suppose the first components are denoted here and the second components are denoted here. If a relation is reflexive, then the diagonal will always be 1 because 1, 1, 2, 2 and 3, 3 must be there. But if I want to represent R2 here, then I must come up with 1 at one more location, 1, 3. So I must come up here, 1, and everything else will be 0. So if an ordered pair belongs to that relation, I'll mark 1. If an ordered pair does not belong to that, then I will mark it 0. But for a reflexive relation or for a relation to be reflexive, the principal diagonal of the corresponding matrix should always be 1. Is that clear? Okay, I want to finish the theory part today, so you people can write these things later. You can always access them once I upload them on Drive. Okay. Symmetric. Now in symmetric relation there is no such requirement that it should be valid for all. Okay. For a symmetric relation, if A comma B belongs to R, then B comma A must belong to R. Okay, which means suppose A is 1, 2, 3. Okay, and suppose R1 is 1, 2, 2, 1. That's fine. R1 is 1, 2, 2, 1. It is reflexive. It is symmetric. Why is it symmetric? Because 1, 2, 2, 1 belong to that. Okay. Go to R2. It's time. Now can I call this a symmetric relation? Yes, I can. Why can I call this symmetric? Because even if I interchange the sequence here or positions here, I'm still going to get the same. Okay? But the main point here is it may not contain certain pairs, or it need not contain all ordered pairs, because otherwise it will become a universal relation. Okay? It need not contain all ordered pairs. So the requirement of the universal quantifier for all is there only for reflexive relations definition and not for symmetric or even for transitive. It's not there. Is that clear? Now for symmetric relation, the matrix that we use to represent it is always symmetric. Now, isn't that beautiful? That the words that we are using, they actually mean the same thing, be it a relation or be it a matrix. Look, for R1 we have said that it is symmetric. 1, 2 belongs to the relation 1, comma 2. 2, comma 1 also belongs to this. Everywhere else you write zeros. Right? What about R2? R2 is also a symmetric matrix, isn't it? R2 is also a symmetric matrix, or the matrix representation of R2, because 1 comma 2 is there, 2 comma 1 is there, and 1 comma 1 is there, but that's okay because that is on the diagonal. In fact, if you refer to the definition of symmetric matrix, they say Aij is equal to Aji. That's exactly what we mean when we define a symmetric relation. Okay, is that clear? But in a symmetric matrix, we expect all things to be non-zero, or even if other things are non-zero, that's fine. But for a symmetric relation, some pairs need not belong to the relation at all. Like for example, here 3 comma 2 does not belong. So because 3 comma 2 does not belong, 2 comma 3 also does not belong. Okay, but that's fine. That's fine. Okay. So is it clear the idea of symmetric relation? Okay. Okay. So any leads for transitive relation? Yes. If A comma B belongs to R, yes. Even here there is no requirement that this should be there for all ordered pairs, otherwise it will become universal relation. Okay, there is no specific requirement, of all ordered pairs. Okay, otherwise it will be universal relation. Otherwise it will be a universal relation, and we don't want that. So suppose A is 1, 2, 3, and suppose I say R as 1, 2 and 2, 3 here. Then what ordered pair I have to include here to make it transitive? 1, 3. Okay, must include 1, 3. Now you might be wondering, can we identify a transitive relation using a matrix? I'm not saying can we represent. We can always represent a relation using a matrix. But can we identify a transitive relation like we could identify a symmetric or a reflexive relation? The answer is no. Okay, it's a bit difficult problem. Okay, so there is no specific matrix. There is no specific matrix associated with a transitive relation. Okay, there is no specific matrix that is associated with a transitive relation. We can represent it. Okay, I can represent this using matrix. I can represent it using a matrix. Where should I write ones? 1, comma 2, 2, comma 3, 1, comma 3. Okay, and it may turn out to be a symmetric or other type. Okay, in this case it's not symmetric, right? It's not symmetric, yes. But it's transitive and it's difficult to recognize the pattern here. There is no specific matrix associated with a transitive relation. So 2 points here. First, there might be some ordered pairs which are totally absent. They are present in the Cartesian product, but they are not present in our relation. That can still be a transitive relation. Okay. Even in the case of symmetric relation, there might be some ordered pairs which belong to the Cartesian product A cross A, but do not belong to our relation. That can still be a symmetric relation. But if we're looking for a reflexive relation, then it has to have all ordered pairs which belong to the Cartesian product which have same components. we cannot even leave 1. Like we left this 3 comma 3 from R1. We did not call it a reflexive relation. It may have additional pairs, but it should definitely have all those ones which have the same first and the second component. Okay? Fine. So keep that in mind. And what is an equivalence relation? It has to be reflexive. It has to be symmetric. It has to be transitive. Okay, then it will be called an equivalence relation. Okay. Fine. Do you know this relation called congruence modulo n? You don't? We had completed discussing relations, equivalence relation, but we did not see any example of an equivalence relation. Correct?
Yes, sir.
So I had asked you whether you know this relation called congruence modulo from number theory. So define it.
Yes.
Okay, congruence model. So we introduce a notation here. Okay, we introduce a notation here, and this notation is when a and b are integers. Okay, a and b are integers, and suppose n is a natural number. Okay, we say that a is congruent to b mod n. Okay, we say that a is congruent to b mod n when a minus b is divisible by n. Okay, let me give you an example on this. 32 is congruent to 12 mod 6. Sorry, not 20, sorry, 20. 32 is congruent to 20 mod 6. Why? Because if I subtract 20 from 32, I will get a number which is 12, and 12 is divisible by 6. Okay, 12 divided by 6 is 2. So we say 32 is congruent to 20. Okay, 32 is congruent to 20 mod 6.
Mod means just absolute value.
No, it doesn't mean that. If you go to the calculator, I had shown this in my video also. If you open that scientific calculator, okay, let it load. This has been a persistent problem today with my net. I'm changing my network. See, you see this mod key here? Okay,
Yes.
that mod is basically this mod. 32 is congruent to 20 mod 6. Yeah, so this basically tells me the remainder that I will get if I divide 32 by 12. Okay? That's not modulus. Modulus is absolute value. That's not this. I'm not aware of it. Okay. Possibly. That's 0. Okay, yeah, so remainder function what you're talking about. Okay, fine. Okay, so we now fix n. Okay, let n be given. Let n be given. Okay, we define R as a relation. Now the ordered pair A comma B belongs to R such that A is congruent to B mod n. Okay. Now we would like to prove that this is an equivalence relation. Okay, congruence modulo n is an equivalence relation. Now how to prove that? Remember, proving any relation to be an equivalence relation involves 3 steps. Okay, what are those 3 steps? First step is that we have to prove that it is a reflexive relation. Okay. Secondly, we have to prove that it is a symmetric relation. And thirdly, we have to prove that it is a transitive relation. Correct? We know that. So let us start with reflexivity here. Okay? Let us start with reflexivity here. Point 1. So I'm going to say let A be any integer. Okay? Let A be any integer. Now, if I considered the ordered pair A comma A, then can I say that A is congruent to a mod n? Yes, I can say that because A minus A is 0 and 0 upon n is an integer. Correct? So it is reflexive. Have you understood this?
Yes.
Okay. Number 2. How do we prove that it is symmetric? Let A comma B belong to R, which means A is congruent to B mod n, which means A minus B must be a multiple of n, where k is another integer. Now what about B minus A? Multiply by minus 1. So B minus A will be n into negative k. Negative k is also an integer. What does that mean? That means B is congruent to A mod n. Essentially this means B comma A also belongs to R. So whenever A comma B belongs to R, so does B comma A. What does that mean? That proves that it is symmetric. Okay, that proves that the relation is symmetric. Now, can we prove that it is transitive? If yes, how can we do that? Let's see. For transitivity, we need to begin with 2 pairs. Okay, so we assume that AB and BC, they belong to our relation R. Okay, so we can write A congruent to B mod n and B congruent to C mod n. Okay. Now, if we interpret it, we can say that A minus B is equal to K1n and B minus C is equal to K2n, where K1 and K2 are integers. We would like to check whether A comma C belongs to this. Okay. Does it belong to R? We would like to check. So we add these 2 equations. Adding the equations, what do we get? B gets cancelled. So A minus C is equal to K1 plus K2 into n. Now look, addition is a closed operation. Addition is closed over the set of integers. Correct? So adding 2 integers never gives any non-integer. It always gives a certain integer. This is called closure property. Okay, we call this closure property. Therefore, K1 plus K2 also belongs to the set of integers, which confirms that A is congruent to C mod n, and therefore it is transitive. So the congruence modulo relation is an equivalence relation. Do you understand this? The notation?
Yes, sir.
Okay. There are other people joined. Meghana, have you understood this? You were not there previously. Rajat, you understood? Okay. Fine, you people can write this down. This question is proving that congruence modulo n is an equivalence relation. Okay, you can write the solution. you can write this.